Don't tell me if you can't hear me. All right. Hello, everyone. So let's get started. Welcome back. Thank you for showing up in person, even though it's raining. So what do you guys do when it snows? You just don't come. Well, I mean, you guys come, but what about the other people? Anyways, so I'd like to start with some announcements. So you have to focus because these announcements are extremely important. I've divided up the announcements actually this time into two categories. So I have a first set of announcements, which I'm going to say are silly announcements. So they're silly because, well, you'll see why they're silly. Am I recording? Yes. Okay. So what I'm going to do starting today is I'm going to be implementing a granola bar office hour. Okay, so what does that entail? I'm sure you're all very curious. So I decided to entice you to come to class and also to come to office hours. We give you granola bars if you come to my office and you ask me excellent questions. And I see that you come to class because obviously I see faces, and if someone comes and is just very hungry and they come to my office for granola bar, that's not going to work out. Okay. And so they're Primo granola bars. They're from Belgium, and they're very expensive. Okay, good. All right. The other thing I'd like to do, this is another silly announcement, is starting from today, I'd like to expand your minds. So why are people still talking? Don't share. Okay, good. Okay. So I'd like to expand your minds. So the way Prakash used to do this is he would give you like 20 history facts within a single minute. And I thought that was amazing, but I don't know anything about it. So I can't really do that. So instead, what I'll be doing is I'll be giving you an Italian expression, a lecture. Okay, because I don't know if you noticed, but my name is very Italian. And so I also speak Italian. Give me a second. I like that you have a question about the silly announcements. Oh, what is not connected to the audio? You're breaking my flow here. Oh, no, it's okay. I've got it handled. Got it. Don't you worry. See, what was I saying now about Italian expressions? Right. I'm Italian. Yes, thank you. Thanks very much. So I'm Italian, and so I know some Italian, and I also know quite a few Italian expressions. And so what I'll do at the start of every lecture to motivate you to come to class is I'll give you an Italian expression. Okay. Hello. All right. And so today's Italian expression is going to be the following. So it's going to be this one. It's basta la pasta, right? Interesting. So what does that actually mean? What is the literal translation of basta la pasta? So I'm sure some of you are Italian and I'm sure you're cringing, but that's okay. So the literal translation is enough pasta. Something an Italian would never say. The actual meaning is enough with these shenanigans, or stop being silly. So I would say stop being silly. Okay, so something my mom would always tell me and still does. So for instance, if I'd like to use this in a sentence, I could say something like, to get serious, Cesare told his 330 students, basta la pasta. Okay, so moving on. Moving on now to the serious announcements. So the serious announcements of today are that I posted an extra note. I posted this on Saturday and then I updated on Sunday. And the note is a more rigorous proof about why the family of languages accepted by DFA is equal to the family of languages accepted by NFA is equal to the family of languages accepted by NFA with epsilon transitions. Hello. Okay, so that's one thing. So I worked really hard on making that note very nice. So please do look at it. There's an induction proof at the beginning, and I think there's one towards the middle, and that'll help you out because in assignment 2, you're going to have a few inductions to do. And so that'll give you a good idea of how to do those. And so speaking of assignment 2, I will be releasing assignment 2 early as requested by some people. So I will be releasing assignment 2 early. Oops, early. So what does early mean? It means I'll post it today. So then you can work on it, and no, I will not change the due date to be earlier. Right? So it's the same due date. I'm not mean. Okay, good, excellent. I have everyone's attention. So that's the trick to get people to quiet down. I give you an Italian expression. Okay, good. So off to the actual material of today's class. Today, what I want to talk about is closure properties of regular languages. Okay, and so I introduced this towards the very end of the last class on Thursday, but no one was paying attention. Everyone was packing, which is very unfortunate. And so I have to sort of remind you again what closure properties are. So to do that, I'd like to just recap what a regular language is. So I'll use REG to denote the family of regular languages. And so we defined in lecture 3 that a language is regular if there exists a DFA that accepts it, right? So that was the initial definition. And then in lecture 4, we saw that actually there's this equivalent machine known as the NFA. And so recall the difference between an NFA and a DFA. Oops, recording. What? Oh, I see. All right. Okay. Everything's okay. So remember the difference between the DFA and the NFA. The DFA is uniquely determined. Its behavior is uniquely determined by the state it's in and by the letter it's reading, whereas an NFA has the ability to choose, right? But we saw in lecture 5 that actually these two things are exactly equivalent. You can convert an NFA to a DFA by considering all the possibilities and putting all the possibilities in states, right, of a DFA. And so these were equivalent. And also the NFAs we saw were equivalent to NFAs with epsilon transitions, right? And the reasoning behind that is that epsilon transitions don't give you much, they just give you convenience. And to see a more formal proof, that's the note that I posted here. So now, these are the 3 computational machines that you can create to prove that a language is regular. Now we're going to see that there's a different way to prove that a language is regular using closure properties. So I'll say that this is a new feature. A bit annoying sound. Okay, I think that might be better. At least it's less annoying for me. Okay, so closure properties. So the way you can use closure properties to prove that a language is regular is, well, suppose you want to show that L prime is regular. Okay. Yeah. It's all good. Yeah. No, it's recorded. Everything's good. Yeah. This is the second person that asked me this. Well, you guys really want the recordings. That's good. What was I saying now? Show that L prime is regular. So you want to show that some language L prime is regular. And so in the previous lectures, what we had done is we just created straight up a computational machine. Now, instead, what we're going to do is we're going to try to manipulate a language we already know is regular by applying some operator. And if this operator preserves regularity and it's equal to L prime, then we've already shown that L prime is regular. So what we're going to do is we're going to apply some operator. And I'll denote the operator as theta. I'll apply this operator theta to L such that L prime is taking theta and applying it to L. And then we've shown that L prime is regular if theta preserves regularity. So in other words, regular languages are closed under the operator theta, then L prime is regular. Okay, this is going to be the new way of doing things. Give me a second. Yeah, question, yeah. Oh, yes, absolutely, yes. Thank you, sorry. Was that the same question? Okay. Okay, good. All right. Good, so that's the general setup. That's what we're going to be doing. And so to do this, I'd like to start with an example. So I'd like to start with an example. So to do this, I'm going to do a lecture callback. I'm going to call back to lecture 3. So recall the language L, which was the language of the alphabet 0, 1, such that W had an odd, or W has an odd number of ones, right? So this language L contains all the strings over the alphabet 0, 1, such that the strings have an odd number of ones. And so remember, we know that this language is regular, right? Because we created a DFA in lecture 3 that accepts it. So we know L is regular. We know L is regular. Since we have the following DFA M that accepts it, right? So we have M, which is a DFA with 2 states. And it has self loops on the states for the letter 0 and transitions back and forth with the letter 1. Right? And so remember what we had said in lecture 3 is that these states were responsible for remembering different pieces of information. So in particular, Q0 was responsible for tracking and sort of gobbling up the even number of ones. And Q1 was responsible for gobbling up the odd number of ones, right? So effectively, I've created a parity checker. And so we said that because our machine was interested in accepting strings that had an odd number of ones, we made the state Q1 be an accept state, right? So now, so that's the setup. Now, suppose I ask you to prove that L prime, which is a set of strings over the alphabet 0, 1, for which those strings have an even number of ones. Okay. Well, what do we notice about L prime? What's the relationship between L prime and L? Yeah. Complement. Very good. Excellent. So L prime is the complement of L, right? So we notice that L prime is the complement of L, right? So remember, the complement is if you take a set and you apply the complement, you get another set, which is all the strings that aren't in that initial set, right? So L prime is clearly the complement of L because take any string in L prime, it's not in L, and take any string in L, it's not in L prime, right? So these two things are disjoint, and together the union is sigma star. So we notice that L prime is L complement. And so if we want to prove that this language is regular, what we could have done before this lecture is we could have created a new DFA or NFA or whatever to accept it, right? But now what I'm going to do is I can immediately take the machine I had started with M, and I can manipulate it such that I accept the language L prime. Okay, so how am I going to do that? Let me just copy over M. I'll copy over M here. Right, so remember, this is the machine M that accepts L. So now, if I have a machine M that accepts a language L, there's a very easy and very simple way of converting it to a machine that accepts the complement. And that procedure is the following. You take all the accept states of the machine and you make them not accept states. So Q1 is no longer an accept state. And you take all the non-accept states and you make them accept states. Right? So in this case, Q0 becomes an accept state, right? And now I've created a machine M prime such that the language accepted by M prime is L complement, okay? And so why is this sort of intuitive? Let's compare our two DFAs with a string. So let's use the string W0, 1, 0, 0. So in this machine, in this machine M, if I have W0 is 1, 0, 0, then what happens? Well, I start at my start state, I read a 1, then I read a 0, then I read a 0. So I end in Q1. Q1 is an accept state. And so that means that in M, Q0 gets accepted. But now if I go back to M prime and M are exactly the same machine, right? The only difference is that if I ended up in an accept state in M, I end up not in an accept state in M prime, which means that I reject that string, right? So W0, 1, 0, 0, this machine M prime reads this string. So 1, 0, 0. It ends up in the exact same spot M had ended up in, namely Q1. But now because Q1 is not an accept state, W0 in the machine M prime gets rejected. Okay. And you can do the same thing for, let's say, a rejection case for M. So suppose I use 101. So 101, I give this to my machine M. So it reads a 1, then it reads a 0, then it reads a 1. So it ends up in Q0. Q0 is not an accept state, and so it rejects. So it gets rejected here. In M prime, W1 ends up, M prime ends up back in Q0 when it reads W1. But now Q0 is an accept state. So W1 is accepted. Excuse me. Thanks. Okay, good. Any, questions? Yeah, that's okay. Yeah, how many ones does the empty string have? And 0 is? Good. Okay. One more question. Yeah, Jules? Yeah. Yeah, we'll see a proof. Yeah, this works in general. Yeah. Good question. Yeah. Where this doesn't work, actually, and I'll leave this as an exercise for you. So I'll leave this as an exercise. So I'll write for you because the only time people have asked me about exercises is when I've written for you. So maybe you don't think that when I write exercise and then for you, it's not actually for you. This is not true. For NFA. So I invite you to try to see why. Okay. But now what I want to do is I want to make a more general claim about what I just showed. So I want to say that this procedure holds for an arbitrary DFAM. Okay. And so what I needed to do, effectively, what I need to do is I need to show that regular languages are closed under the complement. Right? So because that means that if my language L is regular and I take L complement, that's still going to be regular. So that's what I've shown here, right? But I want to show that this is true in general. So the claim I'm going to claim is given some alphabet sigma, if L is a language of the alphabet and L is regular, then L complement is also regular. So the other way of saying this is that regular languages are closed under the complement. Okay. So how am I going to do this? Well, this is a more general claim, right? So I can't pick a particular machine. I need to start with an arbitrary DFAM. So the proof is, suppose I'm given some language of the alphabet sigma, where L is regular. Well, what does this imply, right? This implies that there exists a DFAM, and I'll write it out explicitly. I have a DFAM such that the language accepted by M is L, right? This is just by definition of regularity. And so the idea is the first thing I'm going to do is I'm going to construct a machine M prime such that that machine accepts L complement. So I'm going to construct this explicitly, and this is what I want you to do in your assignment. Please don't put pictures, put an explicit construction. So I need to construct a DFA M prime. So I'll write it out explicitly. Such that the language accepted by M prime is L complement. Okay, so you'll notice that here I have Q prime, delta prime, S prime, F prime. I have the same alphabet, which makes sense, right? The input alphabet doesn't change from the machine that accepts the initial language and the machine that accepts the complement. So we're assuming we're in the same alphabet throughout. Okay. So how am I going to do this? I need to assign these variables in my 5-tuple something. And so what I'm going to do is I'm going to say my machine M prime is going to be exactly the same, except that for the set of accept states F prime, it's just going to be the complement of F, right? So Q prime is going to be assigned Q, delta prime is going to be assigned delta, S prime is going to be assigned S, or S naught, sorry. And F prime, so this is the only change, F prime is going to be F complement, or in other words, Q different F, right? So I take all of the states in my machine M which weren't accept states, and I make those the accept states, right? And all of the states that were accept states in M, I no longer make those accept states. So this is exactly the explicit construction of what I've just said verbally. Okay. So this is a construction. Now I need to prove correctness. This is going to be the only time that I prove correctness for these types of problems, because it's not, it's a bit tedious. So I need to show correctness of the machine. So in other words, I need to show that the language accepted by M prime is indeed L complement, or in other words, it's the complement of L of M, right? So the reason why I'm doing this proof is because it's super easy. So that's nice for me and that's nice for you. So how am I going to show this? Well, what I need to do is I need to show that if a string is in L of M prime, then it's in L of M complement, right? So I need to establish an if and only if, right? So now let's suppose that X is some string defined over the alphabet sigma. And let's say that X belongs to L of M prime. Well, what does this mean by definition? This means by definition that if I take the extended transition function of M prime, I started at S prime and I read X, then I end up in one of the final states of M prime, right? So notice that these are all the superscripts for M prime. So I'm talking about M prime, which makes sense because I'm saying X is in L of M prime. So now all that I'm going to do in this next step is I'm just going to replace, right? I'm going to replace S prime by what it was with respect to M. And I'm going to do that for every of the other variables in here. So for instance, delta prime, well, I know that delta prime is exactly the same as delta from M. So I'm going to reassign this to delta star. S prime is S naught. The only difference here is that F prime becomes Q minus F, right? So it becomes Q minus F. But so now what this means is that in my original machine, right? If my original machine starts at S naught and it reads X, it ends up in not an accept state, right? This is not an accept state. Right? So in other words, give me a second. In other words, this means that delta star S naught X does not belong to F, right? So it doesn't belong to the set of accept states of M. And so by definition, that means that X is not in the language accepted by M, right? So most of these steps were by definition, and this step was just replacing. Okay, and that completes the proof. So I can actually draw a box and feel safe about it. Yeah, Owen, yeah. Yeah. I understand the question. Yeah. So the question is, how can you apply delta prime to So I think the general question is there seems to be a mismatch between delta prime and delta, right? Because they're different machines, so how can you talk about them in the same way? Well, that's because M prime is a copy of N. So it's exactly the same machine, right? So you'll notice, if you go back here, this was M, and this was M prime. They're exactly the same machine. So they have exactly the same states, exactly the same transition function delta, exactly the same start state. It's just that I've relabeled the accept and not accept states. So I can talk about them, I can talk about delta prime and delta the same because it's exactly the same function, right? Yeah. This isn't true in general. You'll see other proofs of closure properties aren't this nice and easy. Yeah. Okay. Any other questions about this? No? All right. So what I've done, therefore, is I've illustrated an example of a closure property. Now what I'm going to do is I'm going to define closure properties in general, and we're going to go through a few more of these proofs. Okay, so let me give you a formal definition of closure properties of regular languages. Okay, so suppose we're given some alphabet sigma and a binary language operator theta. So I'm defining this for binary language operators, but it holds for n array for n greater or equal to 1. And so if theta is a binary language operator, that means that it intakes 2 languages and it returns another language, right? And so we say that regular languages are closed under the operator theta if the following is true. For every pairs of languages, defined over the alphabet sigma, if L1 is regular and L2 is regular, then L1 theta L2 is also regular. Okay. And so this is a very common thing to talk about in math. You've probably seen this in linear algebra and in other classes where you talk about how vector spaces are closed under something. And so it's the same idea for regular languages. Okay. And like I said before, so this generalizes to n array operators. Okay. So I'm not saying anything complicated. I'm just saying I have any arbitrary languages, any arbitrary pairs of languages. I apply an operator to them. This resulting language is always regular. That means that this operator preserves regularity, right? So it doesn't do anything to sort of take you out of the family of regular languages. So now I'd like to illustrate this by sort of showing you some common regular language closure properties. So some common regular language closure properties. So the setup is going to be, let's be given some alphabet and then some languages over that alphabet, and we know that these 2 languages are regular. Then we have the following closure properties. So if L1 and L2 are regular, then so is L1 union L2. So I talked about that at the end of lecture 5. L1 intersect L2 is regular. L1 complement is regular, so we just proved that. L1 concat L2 is regular. And L1 star is regular. So all of these things are regular. Okay. And so we're gonna prove why, but the general idea is, you're saying that L1, L2 is regular, then this is regular, this is regular, this is regular, and so are these two others, right? Hopefully this isn't anything complicated. So how do I prove that languages are closed under some operator? So let's write this under proof technique. So let's see, how do I start this? Proving, right? So proving that languages are closed, or regular languages, sorry, under some operator some binary operator theta, right? And so this technique applies to n area, right? So it applies if theta can only take a single language as an input, or 3 languages as an input, or whatever, right? So the general proof technique is, well, the first thing you need to do is you need a setup, and the setup is, let's just assume, so we assume that L1, L2 are regular, right? So let me just specify, let's suppose we're given some alphabet, right? And so what does this imply, that L1 and L2 are regular? It implies that we have DFA, M1 and M2, such that the language accepted by M1 is L1, and the language accepted by M2 is L2, right? So all I've written is I've just written what I'm assuming and what this assumption means by definition. Okay. So the crux of the proof is really step 2, is I need to use M1 and M2 to construct, or I'll write to create a DFA, NFA, or NFA with epsilon transitions. And I'll call that sort of more complicated machine M prime, such that the language accepted by M prime is L1 theta L2. Okay. And so this is, right, this is the general thing that you need to do, but of course this is very, like, it's a case-by-case thing. So I can't just give you a general rule. You kind of have to see examples, and that's what we're going to do in a second. And the last thing, for it to be a proper, correct, very rigorous proof, is you need to show correctness. But because I don't want you to suffer, I'm not gonna ask you to show correctness. So show correctness of M prime. So I'm not going to show you to do this. I'm not going to ask you to do this, but this is always very good as sort of a way of double checking whether the logic of your machine M prime is correct. So this is a good way of checking M prime's logic. Okay. So this is a general proof technique. It's likely that this doesn't make all that much sense, really. I'm just writing down what I did for L complement. Now I'm going to show you a few more examples where I'm going to construct machines for, I think I'm going to do L1 union L2 and L1 concat L2. Okay, so let's write proofs. And just to be safe, let's say that there's sketches. So I'm gonna start by my assumption, right? So remember what I'm doing. I like to remind you all the time, but remember, I'm trying to prove this statement here, basically. Right? And in particular, I'm going to try to prove this statement and this statement. And so I need to start by saying what my assumption is. So my assumption is going to be, suppose L1, L2 are regular. Let's move this over here. So what this implies is that there exists DFA M1 and M2. And now this is when I'm going to start to write them out explicitly. So M1 is going to be Q1 sigma delta 1 S1 F1. And M2 is going to be Q2 sigma delta 2 S2 F2. Right? So these are two DFAs. These are two DFAs for which the language accepted by M1 is L1 and the language accepted by M2 is L2. Okay. All right. So now what I want to do is I want to use this setup. Let's put back here. I want to use this setup to prove that L1 union L2 is regular. Okay. So let's just draw out my two machines, M1 and M2. Okay, so I have two machines, M1 and M2. They're machines for some pair of arbitrary regular languages, right? So they have, maybe some accept states here. This guy has maybe two accept states here. They have transitions. Okay. So now how can I take M1 and M2 and combine them in such a way that I create a bigger machine? So I create a bigger machine M prime such that the language accepted by M prime is L1 union L2. Any ideas? Yeah.
Like 3 times, like here 3 times, feel like we would be up every.
Very easy.
I mean, we like each state of M1, you date every other state of M1.
No, I don't want that. It's a much simpler construction. Yeah. Combination of, what is the combination of the? I need more than that. Yeah.
The NFA is just these two DFA where you have multiple start states.
Yeah, what are the start states?
The start state is M1.
Very good, excellent. Very, very good. Awesome. So the machine M prime is just going to be this DFA and this DFA, but now it's going to have two start states, right? M prime is going to have this start state, the start state of M1, and this start state, the start state of M2. Okay. And that makes sense, right? Because if I have my machine M prime and I give it some string X, then M prime is going to choose, okay, either I give you to M1 or to M2. If I give you to M1, M1 is going to run through its computation with X. If it accepts, then that's great. That means that it was in the union. If it doesn't, then maybe I made a mistake. Let me try M2. So I give X to M2. M2 runs X. If it ends up in an accept state, that means it was in the union. If not, that means it was never going to be in the union in the first place, right? Give me a second. Let me just write out the explicit form. Okay, so if we want to write that out explicitly, right? So we'll build an NFA M prime. Well, let me not write such that again. Let me actually do it. So M prime is going to be Q prime, sigma, delta prime, S prime, F prime, right? And so now I need to build this machine explicitly. So the set of states of my machine M prime, well, that's just going to be the set of states of M1 and the set of states of M2, right? And so what I'm describing is the union of those sets. So it's the union of those sets. Then what is the set of start states going to be? It's going to be the start state of M1 and the start state of M2. So S prime is going to be S1 and S2. Maybe I should write them recursively. S1 and S2. And then the set of accept states, well, it's going to be the set of accept states of M1 and the set of accept states of M2. So what I'm describing in this case is F1 union F2. So the only thing I need to do, that's the only thing that's left to do, is I need to define delta prime, right? I don't need to define the input alphabet. I'm assuming it's the same as the input alphabet of both DFAs, which are the same. So how am I going to define delta prime? Well, delta prime, right, is a function. It takes a state and a letter. So let's write that out. It takes a state and a letter. And now I need to sort of create a piecewise function, because depending on whether my machine M prime picked to go to M1 or M2, I need to behave differently, right? So if Q is a state from Q1, then what I'm going to do is I'm going to behave like M1 would. And so how does M1 behave? It behaves based on its transition function delta 1. Right? So I'm going to use delta 1, QA. If instead my state is in Q2, then I'm going to use delta 2 to sort of transition accordingly. Okay. And that completes the construction. Or does it? There's a slight typo here. Can someone see where the typo is? It's in delta prime. Well, I know you know. So does anyone else venture a guess? Okay, Louis. That's right. Very good. Excellent. Exactly. So delta prime is meant to return a set of states. And there's a very easy fix for this, because clearly at the moment, this isn't a set of states. So what I need to do is I need to enclose this in a set. Good. Very good, Louis. Okay. Any questions about this? Yeah.
Is what allows us to do this construction of taking two days and taking to say this is an accurate representation of whatever object we're looking on. Is that relying on the fact that I don't think we want to do
So the question is, what allows me to make, right? What allows me to make this construction is that I'm just following, I'm complying with the definition that I did, right? So as long as I create a machine that complies with the definition there. So it doesn't matter if I'm creating a machine from scratch or whether I'm just recycling state from two other machines. So as long as I follow the definition, I'm allowed to do anything I want to do. Because this is a proper NFA, right? I'm meeting the sort of functional requirements of my NFA, and so everything's fine. Yeah. Maybe we can talk about it more. Other questions? Okay, so moving on. Let's do another one. Oh, actually, no. First, before I do that, let me just remark something. Is we've sort of implicitly proven something else, right? We've implicitly proven that regular languages are closed under the intersection. So remark, we've just proved that regular languages are closed under the intersection. Why have we done this? Because we've proved that they're closed under the complement and the union, and that immediately helps us show that they're closed under the intersection. So what do I mean by that? Well, let's take two languages, L1 and L2, and let's apply the complement to both of them, right? So if these two languages are regular, then their complements are also regular. Now I have two regular languages and I'll union them together, right? That's still regular because the union of regular languages, that's still regular. So I have a regular language and I apply the complement to all of that. And that ends up giving me L1 intersect L2. And you can check that with De Morgan's law and sort of the double complement. Okay. So the next example I'd like to do is L1 concat L2. So L1 concat L2, again, this is the setup. I have two machines. I have my machine M1 and I have my machine M2. Okay. And I want to create a machine M prime. I'm going to create a machine M prime that accepts L1 concat L2, or in other words, L M of M1 concat L of M2. Yeah. Right. So I want to create M prime such that the language accepted by M prime is L1 concat L2, or L of M1 concat L of M2. Okay, any ideas? Yeah, very good, excellent, very good, excellent, yes. So let me just show the reasoning behind that, but excellent, yeah. So suppose I have two strings. I have the string x in L1 and I have the string y in L2, right? Then by definition, this means that x, y is in L1, L2. And so what my machine M prime needs to do, it needs to accept this string. Well, how is it going to do this? Well, x is in L1. That means that if I give x to M1, it runs through some computation and it ends in some accept state. Well, let's just show that, right? Given x, M1 reaches some accept state. And given y, M2 reaches some accept state. So now all I really need to do is I need to sort of connect these two paths together, right? And so to do that, what I'm going to say is I'm going to say, take any accept state and connect it using an epsilon transition to the start state. So I connect it to the start state, and I do the same thing for all of the other accept states of M1. And so there's one more thing left for me to do, is I need to make the accept states of M prime only the accept states of M2, because I want to force M prime to accept strings in L1 concat M2, right? And so that means that I'm no longer going to make this an accept state, and I'm no longer going to make this an accept state. So now if I give my machine xy, right, I give my machine M prime xy, M prime is going to say, okay, well, I'll start at M1, I'll read this x, then I'll jump to M2, and I'll read the y and end in an accept state. And so that's exactly what I wanted to do. Let me write the explicit construction and then you ask the question. So how do I write this explicitly? So I need to construct an NFA with epsilon transitions, which I'll denote N prime. So this is actually a 6-tuple, so please check out the notes to see why exactly I wrote down a 6-tuple. But all it's really specifying, it's specifying that epsilon is now the sort of special symbol to denote epsilon transitions. Okay, so how am I going to define this machine? Well, Q prime is going to be defined as the union of the states of both machines, right? Because what I'm doing is I'm using both of the machines together. And so the states of M prime are going to be the states of both. So Q prime is going to be assigned Q1, union Q2. Then the start state of N prime, well, I know that I want to start at M1, right? I want to start at M1 because I want my strings to start with strings, from L1 and end with strings from L2. So that means that S prime has to be S1, the set containing this. Then the set of accept states, those are going to be assigned F2, right? Because I only want the accept states to be in the second machine. And now the last, slightly more complicated thing to do is to define delta prime. Let me make sure. So how am I going to define delta prime? It's again going to be a piecewise function. Hello. That takes a state and a letter. And now the behavior is going to change based on what state you're in, whether you're in a state from M1 or M2, and whether you're reading a epsilon, right? So if you're in state Q1, if Q is a state from M1, and A is a letter, right? So A belongs to this set of letters, then my machine is just going to normally compute through that letter. So in other words, it's going to use delta 1 to from Q read an A. Okay. Now, yeah, give me a second. The next thing is now, what if Q is in Q1, but now A is no longer a letter, it's actually the epsilon transition, right? Oh, I see. So what I should have specified as well is Q1 is not just in Q is not just in Q1, it's in F1. Right, so it's in one of the accept states of M1, because that's where I want to make the jump. So Q is in one of the accept states of M1, and A is epsilon, right? And so in this case, what I do is I jump to the start state of M2. So this jump is denoted in this fashion. And the last thing I need to do is, well, once I'm in M2, I just compute through the rest of the machine as M2 would have, right? And so I just compute using delta 2 from state Q, the letter A. Okay, there was a question behind you, actually.
Yeah, I was wondering if that's all belong to.
No, so good question. Okay, thanks, yeah. So epsilon is not in sigma. Yeah, good question, yeah.
I was just curious, it's also a word with NFA, so.
Oh, that's a very good question, right? So why, so basically, I think the more general question is why are we using DFAs to start with? Yeah, more or less. And that's just because DFAs are deterministic, so they make the building of a new machine much simpler. So you could use it with a DFA, but then what would that DFA look like? Because it's some arbitrary language that's regular, and your DFA has the ability to choose, but there's no real concrete way of sort of visualizing that. Right? But at least for a DFA, you know that everything is sort of set in stone, right? So it's much easier to manipulate. Okay. Other questions about this construction? Yeah.
Why I'm still on the side, but stuff is.
Why I couldn't hear the last part. Why?
It's not a fine, like,
If prime is not assigned, it's right there. Oh, because F2 is already set. F2 is a set of accept states.
Okay, so, but as fine is not exact.
Let's take this offline. Yeah. Yeah, this is okay. S1 is the single start state of my machine M1. Yeah. So the substrate 1 denotes DFAs. So I have DFAs M1 and M2. Good? I think it's okay. Yeah, okay. All right. Okay. So an exercise that I'd like you to do is to do the same thing for L1 star. So if you get stuck, this is usually one that's in the CIPSR books, and I also have a video on my website about it. So I'll also post a video. So I'll post an extra video. Let me just go through this. I'll get to you in a second. So the last thing I'd like to remark before we get to slightly less standard closure properties is that closure properties are not bidirectional. So what do I mean by they're not bidirectional? Well, for instance, if L1 union L2 is regular, it does not imply that L1 and L2 are regular. Okay. And I can show you why, right? So why is this true? For now, I'll prove this in a few lectures from now, but the language L1, which is AN, BN, right? So a sequence of A's followed by a sequence of B's where the number of A's and B's are the same. This language turns out to be not regular. I think I had talked about that in lecture 2, actually. And I can use this to sort of create a contradiction, right? To create a contradiction that shows that this is not an if and only if, right? That closure properties are not bidirectional. So how can I do that? Well, let's take L1 and let's take the union with AB star. Well, I'm taking L1 and I'm I'm taking the union with the universe. And so what I get is the universe. Right? And so clearly AB star is regular. We made a machine for it in lecture 4 actually. But L1 is not regular. Right? So if the union of two languages is regular, so in this case it's AB star, it does not imply that both languages will be regular. And in fact, you can also show with a counterexample that it doesn't imply that either language will be regular. So in fact, if L1 union L2 is regular, it does not imply that L1 is regular or that L2 is regular. So that's an excellent question for a true false in a midterm. Okay, so I think I might have to skip this exercise just for time. There was a question. Yeah.
For the delta, way we have like.
Oh, yes, thank you. Oh, thanks very much. Oh, I just forgot that. Thank you, thank you. Yeah, excellent. Thanks for the comment. Thank you very much. Okay. So I would have liked to do this example because it kind of shows you the point of closure properties, but I don't think I have the time. No, I don't. So I'll have to skip it. So I'll just put it as an exercise and then maybe I'll post something to show you. So prove using closure properties that L is regular, where L is going to be a language that I actually gave you at the end of last class. Yeah. Okay, so you can prove this. You can prove that this is regular using probably the easiest way would have been to use a NFA, excuse me, an NFA with epsilon transitions. But now that we have closure properties and that we know that regular languages are closed under the union, the concatenation, and other operations, then we can sort of break this language into smaller pieces, show that each of the individual pieces are regular, and then combine those together and show that L is regular. I don't have time to do that, but I do encourage you to do so. Okay. So for the last part of the lecture, I'd like to look at non-standard closure properties, which will be on your assignment and will hopefully force you to think. I have not reused previous assignment questions because I don't know. Prakash said, oh, you can reuse my assignments, but then I know that you have solutions to them. So. Okay. So in essentially non-standard closure properties, these are closure properties of operations beyond sort of the traditional ones that we saw in lecture 2. So beyond the union, the intersection, and so on, and the ones that we just proved today. So for instance, this is going to be the first non-standard closure property that we see. Suppose L is regular and sigma is AB. So sigma is the alphabet containing letters A and B. We need to show that the following language is regular. Okay. Where the language is going to be applied this interesting non-standard operator, add 1L. So what does add 1L do? It takes strings XY, takes strings XY from L, and it adds a letter to it. So it adds a letter to any string XY in L. So to make this slightly more correct, it's the set of strings X sigma Y such that there exists a sigma in the alphabet for which sorry. For every letter in the alphabet, there exists strings in sigma star for which x, y is an L. Yeah, so that's a more correct. Yeah. So effectively, this notation isn't that sort of informative, but effectively, strings in add one L are strings from L with an added letter at any position. So you add a single letter to the string in L. So for instance, if sigma is AB, and I have some language which I know is regular and it contains AA, then the following strings are going to be in add1L, BAA, ABA, and AAB. These are all going to be in add1L. Why are they all in add1L? Because I take the original string AA from L, and I add a letter to any of its positions. So I can add a letter at the beginning, in the middle, or at the end. And in every case, that string is going to be an add1L by definition. Okay. So now, how can I construct a machine M prime that accepts add1L, given that I know that L is regular? So, solution. Since L is regular, we know that there exists a DFA M, which I'll denote explicitly, such that the language accepted by M is L. Okay, so let me write out, put a box here. This will be M, right? So M has a start state, it has some intermediate states, and it has some accept states. And now suppose I have some string X, Y, and L, right? If I have a string X, Y, and L, then that means that M, when it intakes X, Y, it reads the first part X, and then it reads the second part Y, and that second part ends in an accept state. So now what I want my machine M prime to do is I want it to allow an additional letter. So how can we do that? Well, one naive way of doing this might be to say, well, let's just add a self loop to each of the states with sigma, right? So in other words, self loops with A and B. Well, that's not quite going to work, right? Why is not quite going to work? Because then we're allowing any number of additions, right? So we would allow X, A, Y, but also X, A, Y, right? And that's no good because add1L adds exactly one letter to my string. So instead, what we kind of need is we need some way of distinguishing the first part of the string X and the second part of the string Y. And so to do that, what I'm going to do, and this is a common trick, I'm going to copy over my machine. So I'm going to take this machine and copy it. So now M prime, so this is, let's say, M1, and this is M2. These are copies of the same machine. This is M prime. So now what M prime is going to do is, given some string, right, given some string X sigma Y, which I know should be in add1L, what M prime is going to do is it's going to read this first X in the first part, the first copy of the machine M1. So it's going to read X, right? And then it's going to say, oh, okay, it's time for me to add a letter. So I add a letter and I go to the same state where I was in M1, just now I'm in M2. And then I read the remaining part of the string. So I read Y. Okay, and so that means that this transition should be labeled either A or B. because I allow the addition of any letter. So what that means is that for every state in M1, there's going to be a transition to the same state labeled A or B. And the last thing, and this is similar to what we were doing with the concatenation, is for the final states, right? I don't want my final states to be in M1 because I want to force the machine M prime to find a jump, right? I want to force it to jump from M1 to M2 so that it can add that extra letter. So that means that I'm going to no longer make these except states. Whoops. Okay. And so formally what the construction is going to look like is if I take the NFA, if I say the NFA M prime, which is explicitly Q prime sigma delta prime S0 F prime. So I'm going to construct this explicitly. How am I going to do this? Well, the first thing is I need to create states. So the way I need to do this is I need to copy over the states, right? I need two sets of states for M1 and for M2. Remember, these are copies, right? So they should have exactly the same states. So how can I do this? Well, what I can do is I can sort of index the state Q, right? I can index it with either 1 or 2, let's say. And so what I'll do is I'll take Q and I'll take the Cartesian product with the set 1, 2. And effectively, what this 1, 2 does is it acts as an index, right? So this 1, 2 will act as an index to either M1 or M2. Okay. So the next thing is what's the start state going to be? Well, again, here it has to be a set, right? It has to be a set. But now I've said that I have to start at the first copy of my machine, right? M1. And so what that means is that S0 is going to be a set. And it's going to contain a single state. It's going to contain the state of the original machine M1, right? And so that original machine M1 has as start state S, right? It has at start state S. But because I want to distinguish between starting in the first machine and the second machine, I need to index it with the number 1. Right? So I start at M1. The other thing is what's going to be my set of accept states. The set of accept states are going to be all of the accept states of the original machine, except that they need to be indexed with the machine 2. Right? So in other words, F prime needs to be F cross 2. Right? So this is saying that all my accept states are going to be in this machine. And the last thing I need to do is I need to define my transition function delta prime. So now delta prime is, as usual, going to take a letter. It's also going to take a state, but now I need to represent my state as a tuple, right? Because my states are now tuples of 2 elements. So in particular, they're tuples of a state and a number or an index, right? So I'll use Q to denote the fact that it's from the original sets of states, and N to denote that it's some index, either 1 or 2. So Q is going to be in Q, and N is going to be in either 1 or 2. So what do I need to do, right? Well, remember the logic that I just told you about. I read the string xy, right? So M prime, what it's going to do, or sorry, M prime is going to read x sigma y. So M prime is first going to read the first part in M1, and then jump to M2, and then read the rest in M2. So the way I can say that is, well, if Q is in a set of states, and I'm indexing it with 1, then what I do is I follow the transition function of my original machine. So I use delta. So I follow the transition function, right? And then at some point, I have the choice of jumping, right? I have the choice of jumping to the same state, consuming an extra letter. And so what that means is that at every single state, right? At every single state in machine M1, I have 2 choices. Either I can just keep reading the string, or I can jump to the machine 2. So I jump to the machine 2, and I jump to exactly the same state. Okay. And the last thing is, now that I'm in the second machine indexed by 2, right? So if n is 2, then I just keep on reading, right? I just keep on reading the string. So then the return set is going to be keep reading the string from state Q with the letter sigma and stay in machine 2. Right. And so altogether, this exactly is describing what I described sort of verbally here. Okay. Any questions about this? I know this was a bit more complicated. So this sort of requires you to think about it a bit. It's difficult to sort of immediately grasp it unless you've seen a similar example. Yeah. Or no, not Owen, the person in front of Owen. The delta bit? Yeah. So this delta prime, right? It intakes a state from M prime. The state M prime is a tuple that as its first element has a state from the original machine, and it has an index, right? So the index is telling you whether you're in machine 1 or 2, right? So if you're in machine 1, right, then you can either read the string that you're reading, right? Or you can say, okay, I'm deciding that now what the letter I'm reading is this extra added letter. And so I can decide that actually instead of reading, I'll jump to a state in M2. I'll jump to that state in M2 and continue reading the rest. And so continuing to read the rest is now if I'm indexed at 2, right? If I'm indexed at 2, I just remain in 2 and I keep using the same transition function. Yeah? The sigma, well, sigma is just any letter from the alphabet, right? So this is always going to be the same. Yeah. I'll take one more. Yeah, you in the back. Oh, okay. Yeah, go ahead. No, keep going. This is when you jump, right? When you jump from this state to this state, I'm in state Q, right? So I stay in the same state, but instead of being in machine 1, now I'm in machine 2. Yeah, sigma is the letter you're reading. Yeah, in the far back. Yeah. Yes, absolutely. Yes, thank you very much. Absolutely. Yeah, I just missed that. Yeah, thanks for the comment. So thanks very much for the comment. The comment was here, you have to stay in the machine 1. Yeah, thanks very much. I'll take one more. Yeah. I couldn't hear what you said, sorry.
There's 2 arrows, one for and one for
You need to point, like you need to talk to me. Oh, yeah, okay, sure. But I mean, the actual answer is the actual answer is this. So yeah, you're right. Yeah, there's only a single start state. Yeah. Okay. So I'd like to do one last one, and this one's probably the hardest. So we'll see if I have the time. If not, I'll post something because I'd like to start regular expressions on Thursday. So suppose L1 and L2 are regular, and the alphabet is AB. What I want to do is I want to show that the following is regular. And so the language is going to be shuffle L1, L2. And what shuffle does is that it takes strings in L1 and in L2 of the same length. So these AIs and BIs are letters. and it just intertwines the strings, so it shuffles them up. So then the string in shuffle L1, L2 is A1, B1, A2, B2, and so on until AN, BN. For example, if AAA is in L1 and BBB is in L2, right? Then the string in shuffle L1, L2 is going to be, well, I take this A, then I take this B, then I take this A, then I take this B, then I take, this A, then I take this B. And that string, so AB, 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 is going to be in shuffle L1, L2. Okay. So I need to prove that shuffle L1, L2 is regular. So this is the trickiest proof you've seen today. So what is this going to look like? Let's first see what the intuition should be. So I know that L1 and L2 are regular, so that means that M1 is a DFA that accepts L1. So I'll write M1 is Q1 sigma delta 1 S1 F1. And M2 is the same, but just indexed with 2. Okay. So effectively, that means that I have two boxes, right? Two boxes to represent my machines. I have the box representing M1 and the box representing M2. And now suppose I have the string X, which is A1, AN, and that's in L1, and the string Y, which is B1 to BN, and that's in L2, right? Then because these two strings are in the languages L1 and L2, that means that, for instance, machine M1 reads in A1, and then it reads in A2, and so on until it reaches an accept state, right? And similarly for Y with the machine M2, the machine M2, maybe it reads a B1 here, it reads a B2 here, and so on, and then it reaches an accept state. And so what I'd like to do, right, what I'd like my machine M prime to do, so M prime be desiderata, which is Latin for what I desire, is what I'd like M prime to do is given XY, A1, B1, A2, B2, until AN, BN. What I'd like M prime to do is I'd like it to intake this string, start at M1, read an A1, then switch to M2, read a B1, then switch back to M1, read an A2, then switch back to M2, read the B2, and so on until it reaches an accept state in M1, and then it reaches an accept state in M2. So that's exactly what the logic I wanted to have, and that's exactly how I'm going to write it up. So the way I'm going to write this up is M prime is going to be Q prime sigma delta prime S naught prime. And so the way I need to design my state space for M prime, in this case, I need to design Q prime such that it has three pieces of information. It has the state in Q1, because it needs to remember where it was in the machine M1. It has a state in Q2, because it has to remember where it was in machine M2. And it has an index, right? It has an index, either 1 or 2, to tell it whether it's supposed to be reading a letter from M1 or a letter from M2. So the way I'm going to write that up is that Q prime is going to be Q1 cross Q2 cross the set 1, 2. Okay. So now what's the start state going to be? Well, I need my machine to start at M1, and I want it to be indexed by 1, right? Because the index is going to be whether I'm reading an M1 or an M2. So what that means is S prime is going to be a set of states. It's going to be a single state. In this case, it's a tuple with 3 elements. Okay. And this tuple of 3 elements is going to contain S1, S2, and 1. S1, S2, and 1 because I start at the start state of M1 and at the start state of M2, and the 1 because I'm indexing the machine M1. The other thing is, how do I define my transition function? So I'm almost done. The transition function takes a state. So in this case, the state is a tuple of 3 elements. Okay, it's a tuple of 3 elements. And it changes based on whether it's reading M1 or M2. It's reading in M1 or M2. So if N is 1, if N is 1, what I'm doing is I need to consume input from the machine M1. And so to do that, I'm going to use delta 1, and I'm going to read from P the letter sigma. But I'm going to stay at the same state I was in M2. But now I'm going to switch to the machine M2 so that I can read that additional letter in M2. So I switch to 2. Right? And now instead, if I'm in machine M2, then I need to consume a letter in M2 and then switch back to M1. And so to do that, that means that I'll remember what state I was in M1 for the future, but I'll read the letter sigma using the state in M2, and I'll switch back to the machine M1. Okay. And I'd like you to work this out. So this is a final exercise for you. The set of final states turns out to be the Cartesian product of F1 and F2. So I end up in the accept states of both machines, but I end with index 1. So please check why this is true. Okay. So Thursday, we'll talk about regular expressions, and I'll give you another Italian expression. Thanks very much.